where we tear things apart, we do some reverse engineering, we look at how things work, and we design cool open source projects and products for the audio and MIDI community. Today, as per the last several weeks, we've been following along with designing a replacement control board for the Strymon Deco in particular, but more generally the Strymon small box pedals that were released before they were re-released to have MIDI. Been working on this for a few weeks now. Apologies if you checked out our stream last week. We had an internet dropout that then got resolved, and then when it reconnected, Restream decided, well, that's the end of your stream. I guess that's all you have to say after 4 minutes. So, you know, that was cool. But here we are, and we're starting to get to the sort of the back end of this project where we're looking at PCB placement and routing and just fixing up some bits and pieces in our topology, making any last minute additions to the overall, just form and function, and then bringing it all together. So I'd say within another week or two, we'll be ready to send this away, send the PCB away to get fabbed for a first version board, and then we wait and see and cross our fingers that no power is connected to ground and see what happens. So that's that. As usual, if you guys have any questions or comments or just thoughts or want to say hi, leave it in the chat. Absolutely. I'm looking a little haggard today. It's been a long week, but very excited to just get back to a fun kind of light project that's super interesting. So yeah, on the topic of manufacturing in general, you might find it interesting. We this week are spinning our Bridge 6 and MIDI through Gizmo, the very first open source Gizmo product or project. I actually had to make some alterations to the PCBs for the MIDI through. So this is what I don't have a full panel, but basically the panel was this. I don't know, that's very reflective. This, and then so it was like a 3x2, so 6 boards on a panel, and it was the first time I'd designed a PCB that I myself was going to be running through a pick and place machine. Previously, you send your design off to the manufacturer, just the board, they panelize it however they like. You might specify whether you want V cuts or smooth routed edges, so on and so forth. They say, thank you, sir. We will do that for you. Here's how much it will cost. You'll have your boards in a bit. But yeah, it was a bit of a learning experience, a bit of a learning curve. And there are a few things I didn't expect. One was I just underestimated how flexible FR4 is, which is the fiberglass and epoxy-based substrate that makes up PCBs. So the way I originally had it, again, let me glare, it's really bad for this. Focus, camera, here, jeez. Anyway, if you can see, there's these 2 thin little bits of board connected by what's called mouse bites, and they are basically a section of PCB with small holes drilled through them so that you can easily just break them away like that. And then you've got these little nubs that, you can just break away by hand or with some little pliers, however you want. And you get just this little sort of tiny little rough indent on your board. But apart from that, you can get a smooth routed finish. That's fine, except that at 3 PCBs wide, even with just, minimal pressure, just enough to squish, one of these big connectors, because this is actually really tricky board to assemble as far as board densities go. Trying to just place one of these dip switches in the middle, with just enough force to get a nice bit of squish into the solder paste, there's enough flex in these boards that then just that would noticeably deflect the middle board. Then when the nozzle releases, it would spring back up and cause some issue with displacing smaller components. So we had to change the board design a little bit to be 2x2 with flush-like adjacent PCBs with a V-cut, and then we were still able to get the rounded corners through some clever panelization. But yeah, and that's assembled way better. They're actually, quite difficult boards to reflow. The rest of them are in the assembly area, but if you take a look at this PCB, these are all 3.5mm connectors here, then more up there, then a big black DC connector, then a USB connector, which is a big metal shell, Then all these dip switches here are big, you know, kind of black bodies that will absorb heat, and it's a black PCB with a big ground plane underneath. So this whole thing is basically a big heat sink. And when you have large, dark-colored components, they absorb a lot of heat, and it's very difficult to get that reflow stage and profile curve to follow nicely. And even when you do, it might not be even across a larger panel. So moving to a smaller panel has definitely increased the manufacturability of that. And that's just, you know, I guess lessons that you learn when you're running your own pick and place line and reflow line, and the things that you learn along the way that no one really tells you until you learn them the hard way. So yeah, that's the state of things. So without further ado, let's crack on. Now our project is here. So this is where things are at. So we've got most of our components kind of in there in the assembly. Now I'm not sure exactly when it cut out last week, so hopefully most of this was captured on camera. But we just changed the order of this slightly to accommodate, because there's these, which I just forgot about, through a spanner in the works. There's these 3 mounting holes here, which are used to have like a nylon standoff that also help fasten the audio board in place. And I forgot about this. So anyway, I've kind of accommodated them as best I can. This one here is a little dicey. They don't have like a big screw head on them or anything, so clearance wise it's not a problem. It's just ideally I'd really like a bit more tolerance between these connectors, or you know, these kind of screw fasteners, just for drilling intolerances, manufacturing intolerances, things like that. So yeah, I'm kind of wondering if maybe I might be best off, like if we bring the enclosure in, we've still got a little bit of room to work with, right? So I'm wondering if I might not be best off just raising it up a bit so there's a bit more, you know, that's, what's that, 0.5 millimeter away. If I bring everything up 1.5 millimeters, that gives a reasonable amount of clearance between that connector and there. And then I could maybe swap those around. Anyway, that's sort of neither here nor there. That's going to be pretty last minute stuff. But, you know, this main board's pretty much ready to do layout in. So to our schematic, let's take a look. So there's a couple of changes. We've got our main section here with the Raspberry Pi 2040. Our decoupling capacitors here. We've started on the pinout. We just need to finalize some of that. We've got our serial wire debug connector with the tag connect probe. I'll show you guys that probably you know, when we're assembling and testing the board. We've got our quad spy flash. We've got our potentiometers. Now, something that I didn't initially think about, but will bear further inspection, is the current draw of this PCB. So I made a couple of interesting points, or sort of I realized a couple of interesting things in that whilst the potentiometers, I'm not sure if I mentioned this last week, but you know, on the original board, the potentiometers operate at 5 volts. And I dare say that's because the onboard ADC is running at 5 volts. And that's probably to get, you know, better resolution, less noise, part availability, whatever. But the foot switches and LEDs and the toggle switch use 3.3 volt logic. And so there's no 3.3 volt supply. They just have pull-ups on the main board, which is pretty reasonable to be expected. So there is a 5 volt supply line on here, and it's just enough so that these potentiometers can form voltage dividers. Now these are, let's have a look at what resistance these potentiometers are, because what we need to make sure is that there's actually enough, that 5 volt supply line can deliver enough current to reliably power our board. So let's see what our potentiometers are, resistance they are. Double check that your meter is in fact not connected to the current terminals. All right, so what have we got here? 2.6. Okay, this is actually pretty good news, because it looks like they are 5K pots. So 5 kilo ohm potentiometers. Why I say that's good news for us. Wait, hang on, 1.7K. No, they're not that low. These are doing some kind of funky readings, to be honest here. Let me just take a look at these. So 1.7K. Really? That seems awfully low. I mean, really low impedance. 1 point. Like that's not changing correctly. Really strange here. I just want to kind of double check these measurements I'm getting. All right, so that pin there is okay, 2.5K. Okay, so yeah, they are 5K pots by the looks of things. Turn that all the way to max, and we'll measure the resistance between ground. I was just getting, might have been some bad contacts there. It's just really interesting. I can't seem to get a clean. Oh, this is really strange. The resistance of these pots is quite bizarre. What I'm going to do, actually, this is interesting. I mean, I guess I just went full auto and assumed that they were bog standard linear pots. What we might have to do is connect the control board up, because now I just want to make sure that this current. Oh, I'm on Facecam. Oh no. Thanks, Simon. I was on Facecam. Well, you didn't miss that much. That's fine. I was just going through the schematic. What I am trying to do though is I'm just taking some profiling the onboard potentiometers. So connecting the two boards back together, and I just want to make sure that basically I'm checking what the total resistance of the potentiometers are, because whatever that 5-volt supply line or that voltage reference is going to have to drive enough current for all of the the potentiometers at whatever their total impedance is. So let's say it's 5 kilo ohms. If you have 5 potentiometers all in parallel, that's 1 kilo ohm. And assuming you've got a rock stable, rock solid voltage reference, that I is equal to V on R. Okay, so you don't even need a calculator for this, but for the sake of completeness, so I is equal to 5 divided. Calculator, come on! Why is the Windows calculator so bad sometimes? It just doesn't respond, and you get the point. So it's going to be 5 divided by 1K. So it's going to have to deliver a bit of current, not that much, but at least 5 milliamps. So we're going to have to be careful with our overall current draw, but we'll see how we go. So that's why I want to measure the resistance of these pots, but I'm getting kind of funky readings, to be honest with you. So if I connect up a multimeter, basically what I'm trying to do is measure the resistance from ground to the wiper of the potentiometer. So I'll connect to a ground point here. It's one of the lugs of the pots. And we'll get another alligator clip so we don't have to hold them. All right, and we'll clip onto. I might just use a Nice jump away there. Okay, so let's go to here. I'm going to probe, take a look at this pin here. See a nice solid ground point to clip onto here. Might scrape off some of the. Might just scrape off some of the solder mask and expose the ground plane here to connect to. It's always a good trick. All right, so bear with me. I just need to scrape away some of that with something with a sharp edge on it, so I can. There's nowhere convenient to put a mount an alligator clip, unfortunately. That's better. Nice bit of exposed copper there. I've got a bad alligator clip, ladies and gentlemen. Always. All right. There we go. All right. Now, let's take a look at these suckers. So probing. So it gives me. Oh, unless interesting. Unless that ground. Oh no, there we go. All right, so it's kind of weird. It gives 1.8 kilo ohms at either end, right? I scrape a little bit more. It gives 1.8 kilo ohms at either end and then goes up in the middle, but it's, unless I'm just blatantly missing something, it's like they're not actually acting as regular voltage dividers like I assumed they were, which is going to throw a bit of a potential spanner in the works. That's better. Okay. And then, I mean, I would have just assumed that they sweep from. So they go all the way down to 12 ohms. And we sweep them up, and at the halfway point, they go to 2.4. And then they go back down. So I honestly, I'm a little. Oh, I know. I bet I know what it is. Actually, completely take that back. I'm really not sure, but there'd be some interaction with these other pots, no doubt. I'm really battling to try and work out what's going on with the readings of these potentiometers. They're kind of acting very bizarrely. I'm just trying to measure the resistance across them. But it's really hard because they're so interactive with the other pots. Okay, well, I think that they're obviously quite low impedance. Anyway, we're going to go off the assumption that we have enough current for here, and go from there. We can always tap onto the main DC input if we need to, I guess. Anyway, so I with that in mind, what we might do is, so this is our power section. So very simple. We've just got our voltage in, going through some basic filtering. The actual values of these caps aren't super, critical or thought out at this point. There's some pretty good placeholders. We may not even need the ferrite bead. It's just there to help filter out some noise from the main board if in fact we we need to prevent any interference. So our 3.3 volt regulator out there. So what we might go ahead and do is add in a 5 volt regulator just in case we do need to tap onto the DC input. And then we can have, an alternative power option. So what we might do is just one of these. It's going to add, it's going to copy and paste this. Decoupling on the input there. But that's, of course, not going to be 5 volts. And instead, we're going to call that, it's V in. It's probably going to be 9 volts. So we'll add a 9 volt marker on there. And again, we'll probably copy some of that supply there. There we go. Kind of annoying the way it joins those nets there because I really don't want a break there. Now that's not going to be V in anymore. That is going to be a 9 volt input. Yep, so I'm going to rename that. Okay, so now we can just regulate that 9 volts down to 5 volts if we so desire. Now I'm going to tap it directly to that 5 volt supply there. We're obviously got, the idea is that we'll use one or the other. This isn't an either or powering kind of situation, so we don't need to do any power muxing or anything like that. So you wouldn't do this if you wanted to use both, the ribbon cable power and the DC power and select between them. You'll damage things. Okay, so just note, don't do that. So depending on where they're located, we'll just add probably just a 1 microfarad. There's enough decoupling on the input of that anyway. Can tag along there. And we'll connect those up to our ground. Yep, and then we'll take a 5 volts and put it on that. So it's a quick and dirty option in case, in testing that pin doesn't have enough power. Now, in all likeliness, these pads won't actually be populated with anything, but they're just there so that we can make sure the project powers up, no matter what the current limitations are, or maybe a different board might have different, requirements. So there we are. Now we've also added in something I think could be really cool, and that is MIDI. So this is the module used in MIDI. It's a BLM 205. Now, it's not actually the exact module we're going to be using. If we go to the PCB layout here, where are we? The BLM 205, let's look it up, has an onboard PCB antenna, which is used in most of the MIDI products, used in some of our designs that we're working on. It has this. Let me switch to the side screen. Oh, yeah, it's not going to like that. Hang on. Let me, there we go. Here, it's got this PCB antenna, but if you're doing onboard antennas internal to a metal enclosure, you need to have cutouts and RF windows and things like that, and it's too complicated for this project. So instead, what we're going to use is they have basically the exact same module, but instead of a PCB antenna, it's got this one, the BLM 215. Got an onboard SMA connector, which means you can use an external antenna. So what I'm thinking is that we'll have that module, and then as optionally you can add that's an SMA to a UFL connector and panel mount it, and then you can just add like an external little ducky antenna, a dipole thing. if you want to, and then you've got WIDI. Oh dear, got a meltdown happening out there, unfortunately, poor little guy. So yeah, but we'll just placeholder this module in place. There's no difference between them; they're identical except for that connector option. So yeah, now the only other change I wanted to make is yeah, so here's our pinout. All right, then we've got these connectors here. So one of them, the 8, I've got these 216 and why? Oh, okay, yep. So this 8 pin goes to our TRS and USB board. All right, so we need to add that. And then this 16 pin goes to the main board. All right, so it's going to go realistically something like that. You know, something like, we're going to mirror all of these, and this is the correct pinout. I'm sure we don't. Now, let me just double check connecting these up the right way, because that would be a pain. Yeah, that's foot switch leg. Okay, great. Okay. And I'm just going to double check which one's pin 1 on here. So zooming back out. Yeah, pin 1 there. Beautiful. Okay, so let's just take these 8 and connect them to this part. Our connector. These 8. This isn't the neatest thing in the world. We'll need to go through and tidy that up. But to that connector, now you'll see that we've got our signals populated on this connector here. And I've got these toggle question marks, and therefore I worked out that they're for other designs that use the exact same connector, but for pretty much every other Strymon small box, we chose the odd one out. They have 2 toggle switches up the top there, and that's what those toggle question mark there is for. So we might call that, change that name a little bit. So you got toggle, have toggle A down, perhaps, and toggle A up. And then we'll change that to toggle B down. They might be the wrong way around. We don't have any way of verifying that, so we're going to take a punt, and we've got a 50% chance, don't we? Toggle B up. Cool. Actually, I'm going to change those. Up comes before down on the other one. Maybe that's the scheme they go with. Who knows? But it's a bit of a show in the dark anyway. Cool. So now we've got that connected up. Now our USB TRS board. We need a few things for this. We want some ESD protection, but that's going to be on board to the USB TRS board, so we don't need to worry too much about that. We do need, I believe we need termination resistors for our USB line. USB. Take a look at the hardware design document here. USB. So yeah, full speed or low speed. Storage device, blah blah. 227 ohm resistors, and they need to be, placed close to the chip. So I'm pretty sure I haven't done this already. Oh yeah, I've already got those in place there. Great. So never mind. What else might we need? We can, I'm not actually going to worry about the pinout now, because that's probably going to be the very last thing we do as to which order the pins are connected into. But at a minimum, we will need, let's just add all 8 pins here. So we've got USB, so we're going to need, what do I call those? DUSB N and P for our differential pair naming. So DUSB N, it just helps to know, oh, no, I don't want that big label. Bit of a sanity check as to how many pins, nets we have, and just start laying out that foundation there. So DUSB P. We're going to need, if we go across to our schematic here, all right, so we need a V-bus sense line. And that is so that we don't, our microcontroller can detect. I'm assuming this has a V-bus sense pin, but basically we're detecting when it is connected to a. So what you want to do is you want to make sure that your device isn't powered on and connected via USB to an unpowered host, because what you do then is you can have a voltage on your USB connector going into this unpowered host, which can damage things. So you need a way of detecting whether you have, you do in fact have a voltage on the V-bus, which is provided by the host, and only if you do, then you kind of power things up. Now, I'm not actually too sure if the Raspberry Pi, so if you check out the main screen, that's what we're doing there. I'm going to check if the Raspberry Pi RP2040 V-bus Sense has a V-bus Sense pin. I know on STM32s, they have a dedicated pin. You just leave it undefined, and in USB, it acts that way. On the Pico, all right, so just having a look through here on some forum posts, having a look. So GPIO24 monitors the existence of V-bus. Pico datasheet. Basically just going to copy whatever the Pico does so that life is simple, really. V-bus, okay, so GPIO24 is a V-bus sensor. We're going to need a voltage divider there, of course, because we don't want to put 5 volts into our 3.3 volt connector. There's another reference to V-bus. It'll be V-bus sense. Sense. 24. That's a bit. So GPIO24 monitors the existence of V-bus. I have to pull V-bus down to make sure it's 0 volts if V-bus is not present. No. Oh, okay. So that's just a voltage divider, basically, to make sure that, we don't fry the input there. So if we take a look at these resistors, so you want to you're basically stepping down 5 volts to 3.3 volts. So let's bring up the calculator now. So our voltage divider equation is going to be this bottom resistor divided by the sum of both of these resistors. So 10, I'm just going to leave off the K because it doesn't really matter. So 10 divided by, what's that going to be, 15.6. That gives us, some scaling factor of 0.64. If we multiply that by 5 from our 5 volt reference, we get 3.2 volts out. Quite handy. Personally, I like to use some high value resistors because I use them on other projects. So I like using 24 and 39K resistors, so a little bit higher impedance, but not a big deal. It also reduces your power consumption and power wastage, which is nice. You don't really, the actual accuracy isn't too important. It's just a binary flag. So in this case, I use 24 divided by, 63. Hang on, that's not right. Sorry, 39 divided by 63, multiplied by 5, and we get 3.1 volts, basically. So pretty much the same thing. So they use GPIO pin 24. Thus, we will also use GPIO pin 24. Now, on our USB board, you can see those resistors are already, those resistors are already on our kind of our daughter board, so no need to add them here. But GPIO 24, tell me I haven't used it for something already. I have, of course. Great. Well, I would rather move the PWM pins and just keep as much in line with the Pico design as possible to make firmware simpler. V-bus sense. I'm pretty sure any pin can be PWM, right? RP2040 data sheet. Triple check before I go getting the pin out. I'm pretty sure, yeah, every like, it doesn't really matter what pins you put your PWM on, it can all be routed to that anyway. So but there's these slices and you've just got to double check that. So let me just check the data sheet. So it's page 534 for the PWM section. 534 PWM here. Yeah, I'm just checking like the pin routing and whatnot. Overview. 8 identical slices, 16, all 30 GPIO pins can be driven by the PWM block. Cool. So we can pretty much just put them wherever. I might do a bit of reordering here, just so that everything's nice and continuous. PWM, because we may change these actual pins depending on what's easiest to do routing in. Not set in stone, but I like to just make sure things at least make some sense in the schematic first before moving on to the PCB routing, because the sort of measure twice, cut once, the more work you do here, the more time you'll save yourself in the end. So there we go. That's all looking really nice. Now, the last thing we need to do, so anyway, I'm getting ahead of myself. B-bus sense and our USB data. Now we need TX and RX MIDI. We also need 3.3 volts. So we need TX MIDI. Again, I'm not really too concerned about what order I put these in. RX MIDI, 3.3 volts, and of course ground. Actually, hang on, that should be plus 3v3. Turn the rest of our pins. Cool, and we have one pin spare, obviously, but it's a lot easier to get 8-pin connectors than it is to get 7-pin connectors. So UART, I want to check what pins the UART is on. Let me just I'm just a little bit confusing with the 2040 as to which pins can be which. I've found the data sheet isn't too clear, and because you've got programmable I/O, it's hard to tell which ones are like dedicated UART pins and which ones are like programmable kind of custom pins. Ideally, I want to just use the built-in peripherals. I don't want to muck around with PWIO. The only thing I'll have to use that for is the addressable LEDs, but that's not the end of the world. So here's the Pico output. So yeah, we've got some UART pins. Have I already got UART going on the Pico? No, I haven't. So we need 2 sets of 2 pairs, because we need the MIDI I/O for our 3.5 millimeter connectors. Then we also need another pair of UART for the WIDI jack. So GPIO 1, great. That can be one of our MIDI pairs there. Let's go to like that on there. So GPIO 0 is TX, so UART 0 TX. UART 0 RX. And I'm probably just going to go back here and change these names to match. UART 0 RX, we'll call that. We'll make our 3.5 millimeter, UART 0. Great. And then we've got, going back to this pin out here, GPIO, where's the next one? I mean, we've got what have we got here? Some GPF 4 and 5. We're using those for SPI. 8 and 9, they're free. Let's use 8 and 9. That's UART 1. Great. TX, isn't it? Fat pin 8, yep. UART 1 RX. Okay, cool. Hey, welcome to you guys just tuning in. We're just doing some final pinout management. Oh, excuse me, man. Hay fever's been acting up a bit today, as it usually does. So we've got our 2 sets of MIDI pairs, so it's kind of our TX and RX making up a pair. One for our MIDI module, so we can have built-in Bluetooth for this, and then another for our 3.5mm MIDI. So yeah, that's that. Now the last 2 pins we need is controlling our foot switches. So if you look at our main board, that glare is really troublesome with glossy PCBs, isn't it? But in our main board, we've got our foot switch connectors. Now, the only thing we need to do with those, they have built-in pull-up resistors. So we're going to, but basically we just need to create an open collector or an open drain if we're using MOSFETs versus BJTs. Driver, and all that looks like. So these have built-in pull-up resistors. So what we're doing is we're just creating a single transistor driver that can pull that line down to ground if needed, and then release it. And so that pull-up resistor does the job. And that's pretty much all the foot switch is doing, but in mechanical form. So I think we're putting that here, at least for now. Let's go to transistors. I'm going to use an open drain configuration. So, sorry, let me just blow my nose for a second. Great viewing here, I'm sure. Ugh. All right, let's carry on. Yeah, so we're going to use some transistors. They're going to consume a little bit less current to drive them. I'm just going to pick some generic, jelly bean stuff. I guess I don't even know what I kind of typically use at the moment. All that said, I do use some 2N3904s in a lot of things. Maybe I go the BJT route. I just don't know. What do I want to use? I mean, we can really use anything. We can even just placeholder in here. We'll use some these are jelly bean MOSFETs, so we can really sub them out for whatever we want. It doesn't really matter too much. But all right, what we want to do is double check their pinout. Even though it's there, I want to make sure I'm just using a common pinout. I haven't used the 2N7000s in a little bit. So basically, we're just making sure we can interchange pretty much any small signal FET in there, and it's going to do the job. Where is it? Okay, yep. So that's looking pretty good. I mean, the only question is I'm not exactly sure what the value of the pull-up resistor on there is, to be honest with you. So, I mean, I guess we can add an additional one and not populate it if need be. So anyway, what our topology is going to look like is, let's add a ground pin. You know what I really wish Fusion would do? Have some sort of universal like supply library, which obviously they do. They have their built-in library, but where you can just have dedicated, or even for anything, if you could just create like a little palette, what would be super nice is up on your toolbar in design, if you could use this section here where my cursor is, and have a small palette like preset components, so you can just go bang, and then you've got a ground pin, linked to whatever library it is you want to, and bang, 3.3 volts. That would save so much time. The more I'm thinking about it, the more I really like that idea. That would be fantastic. So we're going to connect the source here of our MOSFET to ground. Now we're going to add a current limiting resistor to the gate of our MOSFET. The reason being, with these FETs, the gate essentially looks like a capacitor. So it's got this input capacitance, and that's going to charge quite quickly. And if you're using something like a microcontroller, which actually can't deliver that much instantaneous current, then you can actually be at risk of overwhelming the microcontroller pin. We don't really care about how fast we're turning. We don't need to slam this thing off and on extremely quickly. Not at all. So we're just going to limit the current going into that to a sensible degree. And then we use 5K ones, whole bunch in this design. Let's use some more so that we don't overwhelm the RP 2040 pin. We'll add a label here. We use these big labels because we've got room. And that's going to go to what I call it, foot switch L. I should call that foot switch L out. It's a bit more clear as to what's going on. So this is going to be, because then what have I called the actual switches on our board? Have I added them? Have I not added our foot switches yet? Oh, no, I have. Yeah, of course. So FS1 and FS2, that's just one calling, FSL, FSR, whatever. Pretty interchangeable there. Let me move. That's squishy. Yeah, so do I toggle B? Probably some inconsistent naming here, but not the end of the world. So we're going to call that FSL. Just trying to rejig the naming here. I know I'm being a little bit pedantic, but I want it to make sense and be a little bit more streamlined. So let's call that FSL signal, SIG. Then it can be FSR SIG. And I'm going to add another pull-up resistor just to be safe. We don't have to populate it, bear in mind. But if we just add, it's going to mean that we can add maybe an extra pull-up resistor to create a stronger pull-up source. If we do, just in case, I'd rather have the footprint there and not use it, even though chances are we don't really need to use it. Let's just add, something generic. Let's call it a 39K. Sure, because it's standard value that I use the 39K because I use it in the V-bus sense, because it's a nice kind of voltage divided value. And then if I need some sort of moderate pull-up resistance, a bit higher than 10K, less than 100K, I just use 39K because I'm using it everywhere else. And that's going to be pulled up to 3.3 volts. There and there. And that's going to be some tags there. What are they? That's FS L out. Yeah. And FSR out. Cool. Great. So there's, I was talking last week before or after it cut off about using like an analog switch IC so it can be more repurposable, but honestly, 2 FETs and 4 resistors, easy as, low parts count. It doesn't matter at all. The only other thing that I realized we forgot is I'd like to actually add some input pins for the LEDs. It's going to be important that we can keep track of the bypass state according to what the main board thinks is bypassed, and then we can kind of synchronize with that. Otherwise, we could find ourselves getting out of sync. So just going to use any old GPIOs here, really. I don't want to use up the ADC channels. can help it, but we might have to. Sure. Let's use these. So that's going to be, actually, I want to add just some protection circuitry to that. Just some inline resistors, I think. Some 1Ks will go nicely. So we might have to get rid of that big label there. It's a bit chunky. There we go. I'll add some more inline resistors. Just clean it up a little bit. Get those labels out of the way. All right. That's kind of annoying and in the way, isn't it? Let's just use some other pins. We'll shift this all down one. All right. Oh, that's a bit of a mouse mishap. Just trying to think. I kind of just completely blanked off as to what it is I was doing. Anyway, let's add some labels to those, and they're going to be, I guess, like LED L in, maybe. Yeah, LED R in. And the behavior of those is going to change depending on the like the actual effect. So for example, if the LED is modulating, you know, in some analog waveform, obviously we're actually, yeah, maybe I should use the built-in ADCs for those LEDs so I could actually monitor if I mean, I'm trying to think off the top of my head, do the Flint or anything else, is there like a Trem or the Lex that has like a modulating LED? It might be useful to connect those to one of the built-in ADCs, or even the ADC that we've already got. Obviously, that might be. No, I'll use the built-in. I'll leave those channels there in case we repurpose this for another project. No, we're going to be reading all the channels anyway. No point using the built-in ADC. We'll save some power. Okay, well, this doesn't need to go here then. Let's move this to another sheet. I guess we'll add it here. So we'll mirror those so that we've got our inputs coming from the left, going to the right, and then we can give this a bit more space. Restore those default positions so it looks a little bit neater. Okay. Stupid nets, just stay where you are. I guess that's, you don't really need to worry about any clamping or anything like that, I suppose. I'm just going to go into ADC. What do we use? So ADC, we'll use 7 and 8. We'll leave 5 and 6 there for something else for a future project, I guess. So ADC, sorry, we'll use 6 and 7 because we only have one spare. 6, in 6, it's labeled. There we go. And ADC in 7. Cool. Okay, so now we've got those basically just sensing our LEDs, just some current limiting resistors, keep everything nice and kosher. Cool. That looks pretty good to me. Going into the ADC channels, I don't think there's anything else that we really need to worry about. Oh, we need our interrupt pins for the foot switch. Oh no, we don't have foot switches coming from those. I think we've ticked every box in terms of signals that we need to connect. We've got we're sending our foot switch toggle outs. Oh, we need the toggle outputs, of course. So we'll just copy this little block here and duplicate that for our toggle. So that's going to be toggle B up, out, just so it's really explicit what each of these signals is doing. Yeah, we're going to have to change this for future projects. So I'm actually going to change those back to just being, toggle question mark 1 and toggle question mark 2. I know I'm backflipping a little bit here, so sorry, but out and out. All right, then I can make that toggle sure down, out, and toggle up, out. Then toggle a sig. So I'm trying to differentiate what's the actual onboard toggle switch that we're, using to actually detect the toggle switch versus what this sort of emulated output and what's driving it. Let's move those away. Let's give that a bit of breathing room there. It's not the cleanest thing in the world. We can neaten it up a bit, I guess, but I'd rather get onto some layout and routing today. Cool. Give that save that. I think that's gonna just about do us. Pretty much got everything there that we need. Let's check something. Okay. Looking good. Let's go to our PCB here. So, okay, a lot of components here to place. So this is actually going to be a pretty good exercise in, the board isn't going to be as sparse as I sort of initially thought. We can give this all some breathing room. All right, so we're on a 5mm. Hey, buddy, you can't come in here, mate. Can you go back out to mommy, please? Good boy. Ah, dear. Joys of working from home. Right, let's change this to our routing grid. Hugo, you can't come in here, mate. All right, so we can probably move this cap there, give it a bit of space. Just trying to make the best use of this space as possible while I can, but don't need to worry about nitpicking that now. Right, that SWD connector, serial wire debug. Where are the pins that it's connected to? They're up there. Ideally, if we could keep that in there somehow, that would be preferable. But the decoupling capacitors and the crystal placement is way more important, way more critical. This is actually relatively slow speed and pretty unimportant as to where it actually goes. So you can put it up there, maybe. That could be quite nice. I am trying to keep this somewhat divided into digital and analog sections of the schematic, so it might have to be a bit of a but again, that's really not super critical. Our foot switches, where's the all right, so switch 4 is, I probably should go and do a rename of these so everything's a little bit more streamlined, but oh well, we can do that later. So 4 is going to be our left foot switch. So that does need to be here somewhere. I'm going to try and match where it is originally on the board as best as I can. It might not be perfectly possible, but that's going to cause some issues, I guess. This is a little tricky. Yeah, it's probably actually going to have to be a, go there. So not go under the ribbon cable somehow. That shouldn't cause an issue. That'll be fine. He said, if it does cause an issue, feel free to let me know. later on. So put those roughly there. What else do we need? Actually, I really need to allow for more space. They can go there, I guess. Yeah, that'll be fine. What I want to do is put our power input section here somewhere. So we've got our, going back to our schematic, we've got this C66, 67, then 38, 40, 36. So basically all of that is going to be of importance. So that's kind of going to go on the input section near the connector, through the ferrite bead, and then into this voltage regulator here. So 67, 66. So move C66. There we go. So that's our big kind of reservoir capacitor. So that to go as close as possible to the connector. And then where's our ferrite bead gone? That was FB1, then 38, 36, 38, 40. Easy to remember. Here we go. It can go, it's going to go about there. Where's that actual voltage input? So it's there. So that needs to be V in, not 5 volts there. So we're going to change that to be V in. Kind of bastardizing the original use of that pin, but oh well, we should be able to make it work. And we'll put that there. We'll have our ferrite bead going there. Then we're going to want, so move C36. There we go. So again, a lot of, we've kind of just gone a scattershot approach here. We've got 100 nanofarad, a 1 microfarad, and then 10 microfarad for some decoupling, and then also like bulk, filtering capacitance, whether we end up populating all of them after some sort of, noise testing and things like that. Yet to be seen, but much better to have the footprints in there and not populate them than need them and not have them. These foot switches are really annoying. I wonder if they can go on the underside. How much clearance is there? Yeah, they can go on the underside of the board, I think. So they can actually really go in, like, as long as they're not. So to make sure that's not under a component. What is the original? So it's like outside of the LED. Whoops, sorry. Outside of the LED a bit. Guess we could move that, and it could just go on this side of the LED. It's not super critical. Could go somewhere there. Yeah, get them out of the way. Then I might flip them so they're on the underside of the board. Just because I don't actually have the correct footprint for this big long connector here, but it takes up quite a bit of space, and I'd rather have that on the underside of the board if possible. And there's enough clearance there, so. Cool. Find another room for that toggle switch. It's not very critical. Then where's our voltage regulator here? So then after this ferrite bead, honestly, that 100. Oh, yeah, no, that needs to go close to our regulator. Then we're going to use these for our filtering. Kind of go somewhere like that. This is all just some rough placement. That needs to go right up snug to our. We actually don't really need that 100 microfarad capacitor. After all that, it's not necessary. Yeah, it's going to do the job. Then, our 3.3 volt regulator can go, and we're going to use probably end up having to use a 4-layer board, I think. With the routing density that we're going to have, it's just going to be a better layout, better quality PCB layout. So, it doesn't need to be super close to the microcontroller because we're going to use a nice ground plane for that. So it can go there. Then where's our here? is our backup, voltage regulator, as I like to call it. Probably should add a pair of pads to that input, because otherwise there's going to be no way to actually get to it. We'll just add a pad, 2x1 header to there. Sort of just tacking it on, so we've got a power connector there should we need it. Great. Now, where did that go? Down there. Yeah, there we go. All right. We'll probably go there somewhere, I'd say. Again, not critical at all. Okay, right out of the way somewhere here, I think, because then all we need is that 5 volt to kind of connect into there, so we can use a trace on our bottom layer somewhere. That's a reset switch, I think. What's S3? Oh, that might be the boot pin, if I'm not mistaken. Oh no, that's reset, and then that boot pin is there. Okay. Give me 1 second. Thanks, delivery. This is actually the chips for this project. So, sorry for the interruption, but funnily enough, this was a Mauser order, and sorry about that noise, a bit unavoidable. The box design, very clever, very clever. Tearaway tabs. But why I'm opening this on stream is because in here we have a couple of reels of resistors that I needed in a hurry. Hugo, you cannot come in here, buddy. No, please go out to Mummy, mate. Do you want to come and help Daddy open some boxes? All right. You got some sultanas, buddy. All right, hold that. Yeah, thanks, mate. Some resistors that I needed rather quickly. Funnily enough, these are the R39, the 39K. Hugo, you cannot touch that, mate. Please don't touch. No, you can't sit up like this. All right. Come in before you go to Granddad's. We've got some 39K and 24K resistors that I forgot to order in my last big component order, therefore Bridge 6 boards. But also we've got some flux in the syringe. But in here we have some RP2040 chips. Fantastic. They arrived. Now they're in a nice ESD safe bag, so I'm not going to actually pop the individual chips out to have a look, but on the tape we have these RP2040s. Fantastic. So they are, what's on the schematic there. So very cool little coincidental arriving of that order. I wish I'd planned it better. Right. Let's get that. It is a train. All right, I need you to go out to Mummy, please, mate. Do you want to sit and do some design work with Daddy? Can you say hello? Hello. Good boy. It's a bit of a washout lighting-wise this morning, isn't it? Sorry, mate. We are designing some PCBs, which is very cool. I cannot remember what we were up to. Connector. Oh, switches. Yes. Okay. So that's our. Where is that? What's S2? Switch. Yeah. So we've got basically our boot select and then our reset switch, and that needs to be near the quad spy, of course. So that makes sense. This can basically just go on the far side of the board. Trying to work out where to put everything. Our 5 volts, backup regulator, I guess, can just go sort of here. This is more for a prototyping. I don't want to have to bodge something on after the fact. So good counting, mate. 5 volts. That's right.
7, 9, 10, 11.
Just put that down there out of the way for now.
19, 20.
Very good counting, buddy. All right.
3.
Oh, you saw? Yeah, that's LED 3. Can you say LED?
LED.
Attaboy.
LED.
LED.
Yes.
Let's hide those ground wires because we're going to use some
LED.
LED. That's right. Now,
It's LED.
got these input decoupling capacitors. Don't we, Hugo? We've got our decoupling capacitors. Very important. Okay. It's always important to have good decoupling, isn't it? Please do not touch that, buddy. This is going to have to get turned around. Input coming in there.
6, 7.
We want the smallest value. Hugo, listen up. This is good rules of thumb for decoupling. Our smallest, we want the smallest capacitor to be as close to our input as possible. So actually pin, that's just our enable pin, and that's not too important. It's the actual power input there, which is pin 1.
Mommy, you want mommy.
Yeah, you want mummy. Well, if you want a mummy, why did you come in here with daddy? Careful.
Mommy.
Okay, can you go out to mummy and close the door, please?
Mommy.
All right, go to mummy.
Open.
Yeah, you can open it and close the door after you, please. Close. Good boy. Thanks, mate. Little visitor for the show. All right. So yeah, it's going to look a little something like this with a ferrite bead chucked into the mix. Probably do a this, and we'll do a that because we want to make sure it's filtered. Something like that. Move this down and out of the way. Probably as out of the way as we're going to get. We need to get that LED signal out of there. Maybe it could be the last one in the chain. Although, no, we don't want that because we might not populate these. May or might not. Yet to be decided. Let's just save that. Always good practice just to save your progress where you're at. Okay. Well, this big bopping Bluetooth module here is probably going to have a lot of say as to where things go. You know what? Honestly, I'm not even going to bother trying to keep separate like analog and digital sections for these potentiometers. They're not sensitive circuitry, and the reality is I'm probably just not going to have room, especially with this woody module thrown in. So it's probably going to go there. Although there, I need to get to those pins, and then your antenna cable's going to go there, run across it, and that'll do. That'll do, donkey. That'll do. Let's move the supporting circuitry for it up. Now I've got this tiny little like 0606, which is imperial, so really in metric LED. It's 1616 RGB LED here, and it's it's smaller than these 2020 LEDs. I'm probably not going to use this package. I'm going to move to a bigger I want a standardized non-addressable RGB LED package that we'll use across all designs, and just you pick one, and that's what's on your reel and your pick and place machine, and that's what you use. So it handles these 2020 LEDs without any issues whatsoever. So I'm thinking that maybe another like a 2020 RGB LED or a 3535, so 3.5 mil square LED could be a good form factor. But it's just on here as an indicator LED for the woody firmware, and it's nice to have it. Now this copper clear area is for the PCB antenna. I'm probably going to make a separate footprint for the the 215 module because we don't actually need that keep out copper. We want the polygon to fill under there, not quite all the way, but reasonably. If you look at the the module itself, that's all ground plane there anyway, so we don't need to worry much about that. So that's our kind of WIDI circuitry. It's going to go up there somewhere. What are these here? These are our op amps for our DAC that we designed by discrete components because we had to. This is getting really, really tight layout wise. Pretty much these need to go in between our 2040 and this connector here, and I don't know where we're going to find room. I think this, giving up on having kind of nice segregated analog and digital sections, it doesn't matter. It really doesn't matter. Now, what would be nice is if we could get the SPI for this connected up on the other side of this board. So what are the pins here? Like 41, 40, 39. Is there any SPI here? Well, that's our ADC, but we're using a separate ADC, so that doesn't matter. Where's that pin out gone of the module? Okay, so up here we've got, there's no SPI anywhere there. I don't want to muck around with the programmable I/O. That's a pain. There's no SPI anywhere. All the SPI's on this side. So we've already got it. This breakout's going to be tricky. Breakout's going to be very tricky. You know what? It's not the end of the world that it's there. It's not ideal. Coincidentally, what is really nice, and I didn't even mean to, our UART TX, 0 TX and RX is going to this connector just here. So that's really nice placement there. We'll kind of skirt around our quad SPI, go over that way. Hunky dory. Okay, so that's not too bad. I think all this might have to move that way a little, which is fine. Move that over that way a bit. Yeah, that's okay. We've got a kind of USB coming down there. Blah, blah, blah. That's good. I'm going to get that out of the way because that doesn't need to be there. Probably better if that goes somewhere there, I'd say. About there. We'll just have to kind of swap those lines over when time allows. Okay. Let's continue on. So we're going to sort of have general power down here. And this is when you're designing your PCBs, really good practice. You don't necessarily want to nitpick over the perfect little detail of every single component, apart from the critical components, like we did with our decoupling and our crystal oscillator. It's important to get those right. Generally we've got power here. We've got our WIDI here because, physically it's really the only place it can go. Then we've got, got to find a place for this, our DACs. So where are our PWM pins? Where are they? Okay, so they're here. That's not too bad, actually, because then we could just send those down to here, have our DAC section here, send it over to our connector. Okay, that's actually pretty good. That's really actually quite good. No idea what those caps are for. Let's get them out of the way. Okay, so these op amps are rail-to-rail op amps. We could use smaller packages, but honestly, we can make it work with these packages, and I'd rather maintain that just ease of manufacturability with the larger pins, easier to inspect, easier to, rework if need be. So they're going to go somewhere there, along with our supporting DAC circuitry, I think is all that. Oh, we are already using some transistors here. That's right, the BSS84s. We're using those as our level shifters, aren't we? Yes. doesn't really matter because they're P channels. And here we're using N channels, so much of a mutt. We can't really repurpose those as our drivers anyway. So all good. We can carry on. That's a lot of components to fit into there. Crikey, I'm a little worried. I'm gonna probably have to get bring all this down and get snug right up into there and make the most of that. Yeah, definitely a 4-layer PCB at this point. Absolutely. Not getting away with a 2-layer PCB for this one. This here is our foot switch emulation. All right, so again, the hard thing is everything needs to go to this connector. Where's the outputs for those? Oh, Granddad's here for pickup. Granddad Day. I want to change those pins. FS2 there is fantastic. FS1 could be better off somewhere here, but not a big deal breaker, not the end of the world. Where's the? I bet they're on here somewhere, aren't they? Those. Oh, I haven't added them. Sorry, I haven't added the signal pins for driving this switch emulation. So we need 4 of those. We're actually getting pretty squishy on GPIO pins here. Well, where's best? Where's this stuff here gonna go? Probably in here too. It would be nice if we could. That crystal oscillator is just in not the best spot, to be honest. I think we might have to rejig this a little bit. We're gonna bring this decoupling cap up a little bit, is what it is. Just don't want anything else going on here around our crystal oscillator. We want to keep that nice and sanitized in terms of placement. It's going to be in and out. So that's pretty nice. Get that decoupling cap out of the way a bit more, maybe a bit close to the chip. Should keep things fairly clean, although they're right next to each other. That's frustrating. Gives us a little bit more space to work with. This can probably be brought a bit closer, in fact. But it really is a challenging pinout to work with. I'm wondering if we can streamline that somehow, but yeah, like I said, challenging pinout, but probably the best we're going to get. Best we're going to get, I'd say. Although what we could do for that load capacitor is move that up there. It blocks that bit off there, but gives us a bit more, margin for error, I guess, there, which is nice. Which was definitely nice. Just musing. Okay, cool. This is just going to get ridiculously crowded very quickly, and I'm not sure how viable it's going to be, really. I think what we might have to do is chuck this so our PWM's there. I'm thinking what we might actually have to do is put our DAC up here and just deal with routing those. Let me turn off the violator warnings. If we put that there. I just realized as well we've got to add some more pins we need for our MIDI jack. Story of today, so we've got our Bluetooth pins. I'm going to change those to, what's that, UART1TX and UART1RX. We've got some test points there. We've got this button. That's not very good, is it? Make it a bit more readable. Okay. We've got this button and our status pins, which are going to help determine, so we can actually read the status and what's going on with our MIDI module. So that's going to be an output, just a standard GPIO pin is going to be fine. Don't really need a current limiting resistor for that, although, can't hurt. but then we've got our status pins, which we need some interrupts for. This is we can purpose these. So if our MIDI jack's up here somewhere, we can use these pins here for that. So that'll be handy. What pins make the most sense to avoid some of this decoupling nonsense going on here? 41, 40, and 39. You know, I like those. We can just go right out of the way here. Let's do that. It's the technical term, by the way. Okay. Use those pins. BLE. What are they called? Oh, yeah, it's all just BLE something. So why isn't the autocomplete showing there? Annoying. All right. BLE status 2 and BLE button. I'm not really going to worry about the current limiting resistor. It's not a. That pin is barely used. It's just going to be used for connecting to stuff. Oh, I lost my monitor. There we go. We're back. That was weird. Cool. As I said, this is getting pretty cramped. Pretty cramped. Trying to work out. I really want to keep the DAC in here, but I'm really wondering if space is going to allow for it. Where to put everything? C39, what's that capacitor floating around there? My power section, C30. Output on our 3.3 volts. No, we don't. It is best practice. It is going to be good. We really don't need that, I don't think. I'm going to leave it just for now, but I don't think we're going to need that. I came into this thinking, oh yeah, this is going to be a really nice, loosey-goosey PCB layout, plenty of room. Not plenty of room, as it turns out. What's this? R17 and whatnot doing here. Pin 2, R17. Here for our foot switch inputs. Okay, so yeah, that needs to go. Could have just looked at the names over this side, and then our debouncing, I guess. Yep, there. So they're going to be lined up with those things there. Then they're going to be debouncing for our toggle switch. So realistically, they can all go up here somewhere. So you're just trying to kind of massage your PCB layout and get things roughly in the right place. So this big tangle of air wires starts becoming a little bit more manageable, and save liberally throughout. Okay. How are we doing? An hour and a half. Pretty dry stream, but this is PCB layout for you. Might go for another 10-15 minutes and then wrap it up. I just want to make some more sense of this. Okay. Can we fit all of that DAC in there? Yes, we can. I'd rather keep that close and try and really jam it in here. I think that'll be better off, and if we can make some more room around there, that should be enough room. Should be. Okay, so that's foot switch emulation is going to get shafted somewhere up there, unfortunately. Now, the other option is, I'm just looking at this fit of this board in here. And there's a whole bunch of room here that isn't being used. I'm wondering if maybe we, in fact, utilize some of that. In fact, we could use that whole section and put a cutout in there. As I'm looking at how this goes together, we definitely could do that. No reason why we can't. So all that wasted space in the middle there that I think we could utilize. So we could probably extend. We'd have to put a cutout in our PCB. That's fine. For our ribbon cable, we can do that. We are going to extend our PCB because I really think we're going to need more space. Honestly, it's just, we can do it. We can definitely fit everything onto this board somehow. It's just how much time is it going to take? How complex is the routing going to get? How likely is that there's going to be an error, or, it's going to make it hard to manufacture, all that sort of stuff. It's going to be better if we can add a bit more space to it. Okay. So 0 thickness line, we're going somewhere from here. Don't know exactly where the foot switches sort of end. So we'll check that in our 3D model, but we'll just, whack a bit on, I guess. So at 26, 50 mil seems like some nice round numbers, and we'll just see what that looks like in our 3D model. Delete that, because that would give us lots of nice room for this, and I'm about that. And put our power management down there out of the way. It'd be really good. Let's push that and see how we're doing space-wise. So you'll start to see the reality of how cramped some of this is becoming in a moment. It doesn't actually look as bad when you're looking at a 3D PCB because there's less clutter, less layers, and document layers and keepouts. There's a lot more going on in the 2D PCB than the 3D PCB. So it doesn't actually look too bad, but trust me, routing it will be quite tricky when we have everything jammed on there. Okay, sure. Let's bring that into our design model. And we always, this is a rough model. I've kind of just hand measured everything, so we don't want to be putting everything to the nearest 0.5 millimeter. Certainly not. I can already see it's going to hit those foot switches, so it's going to be too wide. Yeah. But in terms of it's definitely not too long. We've got lots more room to work with if we want to. And then we could just put the foot switches like there. Yeah, I like that. All right. Don't know why I didn't think that earlier. That's great. Let's move that in by a good bit. Very precise. Units there, 3 mil either side should give us a decent amount of clearance. All right, we can extend that out maybe another 5 mil. Let's see how that goes. I'd rather have more PCB space and then shrink the outline to fit around it than not. But if that area in the enclosure is available, then there's no reason not to use it. None at all. Very funky looking PCB. Oh, when they're out this, they're just going to think, well, this is definitely going around some unmovable parts in an enclosure. Because look at it. It looks disgusting. All that. I'll have to add some corners there so it can actually be routed out by the bits, because you can't get internally those I guess like in the innies versus the outies, you can't get sharp 90 degrees because they're milled out by a milling bit, which is circular. So you can't. So on the edge, you just take some away there and some away there, and you get perfect sharp 90 degrees. But on the inside, it's always going to have some sort of radius. And if you just leave it at sharp 90 degrees, the PCB house will do their best, but it is always going to have some curvature. But if it's best practice to just specify exactly what that radius is so that you have full control over the design. Okay, I'm going to need to round that corner out a bit, that's for sure. But that's looking good. I mean, we've still got more room, but I don't think we're going to need it. Starting to get a bit excessive, and I don't want to push it too much, but plenty of space. Look at that. Lovely. I'm really happy with that. Well, we might leave that there for the stream. Looking at PCB placement, managed to optimize some of the layout. Really happy with that. That's going to mean we can move, just quickly, we can move all of our power circuitry down to, that's all going to come down. Get that ferrite bit as well. Down here, as is all of this. Come down there. move those out of the way. Then yeah, we could put our Bluetooth module. Probably, I mean, we could put it up here because we actually have a bit too much. Oh, I don't want to push that. It's going to go there. Let's say, then we've got all this room for our DAC and our foot switch emulation. Yeah, that's going to be really good. Well, we'll leave it there for today. A little bit of a drier stream, you know, but this is the reality of designing something, looking at your pinout and PCB layout, and sort of the reality of it, what's involved. It's not all fun and games every day, but hope you enjoyed that. I hope you learned something as always, and we'll see you next week for another Teardown Tuesday. Bye for now.